Hello, dear students. As I promised before, I will prepare this video for you for more practice and for those who had a problem of not coming to the class. Uh, Please watch this video to understand the topic of how to balance the assembly line. Before starting the explanation of this type of uh, manufacturing process, assembly line, because the rest of this chapter is theoretical, I just put these slides that are related to the concept of balancing assembly line. So please review the rest of that. This type of manufacturing assembly line, as you review in the previous part, is a set of successive activities or tasks, okay, that starts from beginning to the end, that moves and flows a material or whatever the type of service to give and deliver and hand it to the final client. So to this end, some definitions are important in the concept of assembly line. What are them? Here you can find these three important definitions. Workstation cycle time is a uniform time interval in which a moving conveyor passes a series of workstations. So, as we know, we can define our work based on different workstations. The cycle time is the time that says as a total the whole activities of work station should be that size of time. Okay, so it means that, for example, if our workstation cycle time is 90 seconds, okay, it means that all of the workstations that we have in our company should not exceed of that 90 seconds. Okay, the other definition that is important is rolling the assembly line. To what is the objective of this item? Assignment of tasks to a series of workstations so that the required cycle time is fulfilled and downtime is minimized. So what is the meaning of that? Because when we have some tasks in our company, we don't know in which workstation we should assign them with the aim of increasing the efficiency of the company. So we need to assign them the form that they fulfill the cycle time, the item that I told you in the previous slide. What is the meaning of that? To not exceed that, for example, cycle time that was, as an example, 90 seconds, and minimize the downtime, minimize the idle time. The less the idle time or downtime, the more the efficiency. Okay, so based on the items that we learn in future slides, we review these items. And finally, the third definition is the relationship of precedence. It means the order in which tasks must be performed in an assembly process. Okay, we should define what are the relationships of the tasks in our company. For example, if we have three tasks A, B, C, where do they locate? If B comes after A, or if A comes after B. Okay, so we need to clarify all of these relationships between different tasks. Let's continue. So when we are talking about assembly line, and we talked about the three definitions in the previous slide, to balance this assembly line with the aim of increasing and improving the efficiency of the whole assembly line, we need to balance it and assign different tasks to each workstation. Based on the assignment, we'll learn how many workstations do we need that we'll see in our example. But here, we should follow 6 different steps to balance the assembly line. What are them? Specify the sequential relationships between tasks using a precedence diagram. So normally, guys, I will review this concept from 2 points of view. In our exam or in our examples, as we see in near future, I will give you a list of tasks with the predecessor relationship. Okay, so you should draw it and report it graphically. For example, task A comes after task B, B comes after C, C comes after D, and the rest. Okay, but in the real world, if you work and you want to balance an assembly line as well, after detecting and knowing the tasks, it'll be easier for you to depict these items, okay, in a graphical form to understand better what are these relationships. So the second point is determine the cycle time of workstation. As you remember, when we talked about cycle time, it was the time that from the entering point of this workstation up to the end, up to the exit of the workstation. Okay, it means that we should calculate this one for all of our workstations. So what will be the formula? The formula is production time per day, for sure. We'll see some examples, divided by required output per day. So the result of this division will give us the cycle time. The third point is determine the minimum number of theoretical workers. So as you see, minimum, two keywords, minimum and theoretical. It means that we should calculate what should be the minimum number of the workstations. For example, if the result of this formula, sum of task times divided by cycle time, is 4, it means that as a minimum, we should have 4 stations, 4 workstations in our company. It means that less than 4 is not possible and is not permitted. Maybe more than that happens, but less than that is not possible. So, when we are talking about assignment, we should define based on what rule, based on what decision we need to assign these tasks. So, in this case, as you see in point 4, we should detect and confirm 2 rules, primary rule and secondary rule. Primary rule tells us what will be the priority of assigning the tasks. What is the function of secondary rule? This function of secondary rule is for the time that we have a tie. It means that, for example, based on the primary rule, 2 tasks are equal totally. So now the secondary rule tells us which one should be selected. Important point. If as well the secondary rule gives us a tie, it means that after primary rule tie, after secondary rule tie, it's not important. Arbitrarily, we select and assign those tasks, okay, because they are indifferent. So, point 5, assign tasks one at a time to the first workstation until no more tasks can be added. So what is the meaning of until no more tasks can be added? When we understand no more tasks can be added, always we should compare the total tasks assigned to that workstation up to that moment with the cycle time. So this difference tells us if we can assign a task that fits in this difference or no. We'll see in our example. And Point 6, evaluate the efficiency with this formula. Division of sum of task time by actual number. So when we do the assignment, we'll see what is the number of the workstations, the actual. The other one that we had in T was the theoretical, but maybe the actual, the real number of workstation could be more than that in T. So this formula gives us the efficiency of the the assembly line. But if it's possible to make a change or to improvement, as you see in the seventh point, if the efficiency is not satisfactory, rebalance using a different rule. So we need to change the rule, okay, to see if the efficiency of the system will increase. To understand better this concept that we had in the previous slides, let's review one example that is the J-wagon model will be assembled on a conveyor belt. 500 wagons per day are required. So the output per day is 500 units of this wagon. The production time per day is 420 minutes. So here, easily we can calculate the cycle time based on the formula that we have in the previous one, because we have production time per day and the output per day, 500 and 420. And the assembly steps and the hours of the wagon are given in the following table. In the next slide, we have the more information about each of the tasks of this assembly line. Balance this line to minimize the number of workstations subject to cycle time and precedence restriction. So, guys, always we want to minimize the number of workstations if it's possible. Why? Because mathematically, remember the previous formula. In the efficiency, when we have actual number, real number of stations, if it's smaller, the efficiency will be bigger. Okay, so because the other items are not changed, cycle time and the total sum of time of the tasks. Okay, so if we can balance our model, the form that gives us a minimum number of workstations, we are winner and we have a better efficiency for our system. So to continue the previous slide, that was the explanation of the example, here we have the description and more detailed information about the tasks that are important in this assembly line. So as you see here, guys, this column shows us the different tasks that we have in this assembly line, A to K. So besides, you see all the task times are prepared, 45, 11, 9 to 9. The total of these tasks, if we calculate, it's equal to 195 seconds. Pay attention, seconds. Why it's important? We'll see. The description is not important for us, okay? And predecessor tasks are located here. If, for example, here I have this one, it means that before task A, there is no task. While, for example, if I have here C, it means that before task F, for sure task C comes. So our first step is draw these relationships based on these predecessor tasks in our example to clarify more what we are talking about. Let's go to the next slide. So as you see here, this part above is exactly showing graphically those tasks based on the predecessors. Okay, so as you see, for sure, task B comes after task A, task G comes after task C, task K comes after task J. What is the meaning of that? For example, it means that before completion of task J is not possible to assign task K. This is a relationship between different tasks. So easily you can show this one graphically from the table that is given to you in the previous slide. As I told you in our exam as well, I will give you the table and I will ask you to draw something like this. So the next step is calculate the cycle time of workstation. What was the formula of cycle time? Production time per day divided by amount required per day, or output required per day. But one important item, the key factor here is the production time per day that we have in our example is based on minutes, while the task time here, all of them, is based on seconds. Okay, so pay attention, very important item. Always they should follow and they should have the same unit of time. So if we have here second, here as well we should multiply it by 60 to change it to seconds. As you see here, 25,200 seconds divided by 500 wagons gives us a cycle time 50.4 seconds per wagon. What is the meaning of this? It means that, guys, we can't have workstations more than 50.4 seconds per wagon. It means that all tasks that we assign to that workstation should not be more than 50.4. It could be less than that, but it shouldn't be more than that. Based on our decisions, we try to assign the form that minimize the downtime, the idle time, as we saw before. So the next step is define the theoretical number of workstation. As you remember, the total task time that we had in the previous slide, 195 seconds, divided by the cycle time. It gives us 3.85. We round it to 4. It means that this example should have at least 4 workstations, as I discussed before. Based on this reason, minimum theoretical number of workstations, we can't have, for example, 3 workstations. At least we should have 4 workstations. So let's continue the solution. So as you remember, in our steps, we talked about primary rule and secondary rule, and we talked about the function of each of them. So here we select these two rules. The primary rule prioritizes tasks according to the number of following tasks, and if tie happens, prioritize in order to the longest time. So guys, there are two types of examples or exercises that you can face with them. First one, I give you this primary rule and secondary rule, that this one is primary, that one is secondary. You should follow that one. Or I don't mention which one is primary or secondary. You should know that always we use these two rules. So if I don't mention which one is primary, which one is secondary, it's your decision. You should write this one is my primary, this one is my secondary, and based on that I assign and I balance my assembly line. So if we follow our primary rule and secondary rule based on what we have here, This table shows us the priority of the tasks. Why? Because as you see, for example, task A has 6 following tasks, while task B or D have 5 following tasks, and the rest C or E, F, G, H, I, J, and K. So as you see, for example, here, guys, because B or D, both of them have 5 following tasks, for sure here tie happens, okay? And we need to select our secondary rule based on secondary rule. Okay, let's continue. So, pay attention. It is important to follow the rules, okay, and assign the workstation. Let's start with the first task because the highest priority is task A. So as we see in the previous one and as we have in the table that we had, the task time of task A is 45 minutes. And for sure, we know the cycle time here in our example is 50.4. Okay, 50.4. What is the meaning of that? It means that the total time of the workstation should not be more than 50.4. So when we assign first task, okay, task A, it remains for us only 5.4 seconds, okay, 5.4 seconds. So my question, we still have this 5.4 seconds, sorry. Is it possible to assign more tasks? Let's see. The next tasks that are in our priority are tasks B or D. If we go back to the graphical explanation of the tasks or the table, we'll see the task time of each of these. B is 11 seconds and D is 50 seconds. But before continue this one, pay attention. As you see, the number of following tasks of B or D, both of them is 5 seconds. So what should we do? A tie happened here. We should go to our secondary rule that is saying prioritize in order of the longest time. So when D has 50 seconds of task time and B has 11 seconds, so D has the priority. But can I fit this one in this workstation? Because as we talked before, it remains for us only 5.4. But for sure, we can't fit a task of 50 seconds on this one. The task D, no. And the rest of the tasks, guys, is not possible to assign. Why? Because based on the predecessor relationship, we can't assign the tasks while the predecessor of them are not done yet. So to this end, task A only goes to station 1. So we assign task A. Let's go back to the list of the tasks. The next task based on the rules will be task D, as we discussed before. So if I assign task D with a time of 50 seconds, okay, the idle time will remain 0.4. So the only one that comes after that, okay, the task that we have has for sure a time more than 0.4 seconds. so we can't assign more other tasks to this workstation. So as well, D goes to a one workstation. So up to here, we have two workstations. So we assigned task D as well. Let's continue. The next one, unassigned, still unassigned, is task B. Okay, the task B with five following tasks. Okay, and the task time 11 seconds. So as you see here, guys, if I assign task B, what happens? If I assign task B from the cycle time, it remains for us 39.4 seconds. So, what are the next tasks we assign task B? What are the next tasks? We should see if the next tasks are less than 39.4. Only in this case we can assign them in this workstation. So in the case of C or E, again, tie happens. Why? Because both of them have four following tasks. But pay attention. The task time of E is 15 seconds, while the task time of C is 9 seconds. So between 15 and 9, based on the secondary rule, which one has the priority? Of course, task E. So as you see here, we assign task E. So up to this moment, we completed the time of this workstation to 26 seconds. What remains for us? 24.4. So if again I have a task that fits less than 24.4, I can assign to this same workstation. So the next one, we assign D as well. The next one is C. Of course, we can assign it. We can assign it because it has 9 seconds and is less than 24.4. So if I assign it, it remains for us 15.4. Okay, we assign C. Now, guys, it goes to four different tasks. F, G, H, I. One important item. All of them have two following following tasks. So they are equal in the primary rule. Now we should assign them based on the secondary rule. So based on the secondary rule is it's saying the longest time of task. But if you see in the tables, the longest task time for all of these four tasks is 12 seconds. So as I told you, if this one happens, the tie in the primary and tie in secondary rule, so there is no difference. We assign arbitrarily. So I can assign one of these one, F, G, H, or I. For example, here we assign F. So by assigning F, it remains for us 3.4 in comparison, always in comparison with the cycle time that is 50.4. So I assign F as well. It remains 3.4. What are the next candidates? GHI. Is it possible to assign one of them or all of them or two of them? No, because their task time is 12 seconds and I have only remaining time 3.4. So we can close the station 3 with these with these four tasks, B, E, C, F. Now we should assign the next to the next workstation. So based on the reality that we talked before, we can assign or G or H or I. Okay, So for example, I assign G, with 12 seconds. It remains for us 38.4. I still can assign H, okay, the next one, because it's 12 seconds and I with the same reality, okay? So, and with the same reason. Here I assign 36 seconds and it remains for me 14.4 seconds available. So the next task is task J. Can I assign it? The time of task J is 8, but I have remaining time 14.4. So perfectly I can assign it to this workstation. If I assign this one as well, task J, okay, so the time remains for us is 6.4. Perfect. The only remaining task is task K. The time of this task is 9 seconds, but we have only availability of 6.4 seconds. So we can't assign this one to this workstation and we close it. So obviously we have a fifth workstation that only K enters in it with 9 seconds. Okay, just pay attention, guys. Only here, as we see this 41.4 idle time of the workstation, it means that we have a potential of 41.4 seconds that we are not using. This one will show us that the efficiency is not that high. Okay, that we'll see in our next slide. As you see here in this slide, is just all the explanation that we had in the previous one. We have 5 different workstations. No, workstation 1, 2, 3, 4, and 5. You can make a comparison with the previous slide. And now is the time of calculating the efficiency. As you remember, the formula of efficiency was T divided by the real number of the workstations multiplied by cycle time. So as you see here, NA here is 5, while NT was 4. So you remember this one was minimum. So this 5 is possible because we are not allowed to have less than 4, but we are allowed to have more than 4. Okay, so based on this calculation, the efficiency of the system will be 77%. Good, but not that satisfactory. What should we do? We should change the rules. As you remember, the point 7 of the slide of the steps of a balancing assembly line. As a homework, we have it in the next slide. Let's see. As I told you in the previous slide, as a homework, I asked you to change the rule. How? In the example that we solved, the primary rule was the highest number of following tasks, and secondary rule was the longest task time. In this one, I asked you to change this one. Now, your primary rule is the longest task time, and the secondary rule will be the highest number of following tasks. Please solve it and report the efficiency that you find in this example. As I told you, you can submit this one with the exercises of chapter 1 that gives you a bonus, okay, for those exercises. Have a wonderful time. Goodbye.